All right, ready to dive into some seriously mind-bending philosophy. Today we're tackling Zeno's paradoxes. I'm sure at least a few of you have heard about these, but get ready to have your brain twisted.
And what makes these paradoxes so interesting, especially for a philosopher like yourself, is that they're not just some logical puzzle. They cut right to the core of how we think about like space and time, motion, even
Mm.
reality itself.
Exactly. Okay, so quick refresher for anyone who needs it. Zeno of Elea, ancient Greece, around 490 BC. He was a huge follower of this other philosopher, Parmenides. And Parmenides, he had this really radical idea that reality, it was just this one unchanging thing.
Yeah. And Zeno, he decided to defend Parmenides' philosophy, but instead of just writing a straightforward essay or something, he came up with these paradoxes. They were designed to show that if you believe the world is made up of tons of separate, constantly changing things, well, you end up with some pretty ridiculous conclusions.
And the crazy part is that Zeno's actual writings, they're lost, gone. Thankfully, we have Aristotle to thank for our knowledge of these mind-bending ideas.
Yeah, Aristotle was super meticulous. He documented everything about Zeno's arguments. He knew they were important, not just as like fun logic puzzles, but as these deep, challenging questions about how we understand the world.
So what kind of paradoxes are we talking about here? Well, we're going to explore two main groups, paradoxes of plurality and paradoxes of motion.
So, with the paradoxes of plurality, Zeno's trying to show that even the basic idea of many things existing, it just leads to contradictions. Like, can something be both limited and unlimited at the same time? Does every single thing need to have a size? And if absolutely everything can be divided forever, is there anything left at the very end?
Whoa. Okay, and then there's the paradoxes of motion. These are probably the ones everyone's heard of, right? The runner who can never reach the finish line because they have to cover an infinite number of distances. The arrow flying through the air that's actually at rest.
Yep, those ones. They really make you question everything you thought you knew about how the world works. The gap between our everyday experiences and what logic and math seem to be telling us.
Okay, let's start with one of the paradoxes of plurality.
Hmm.
The argument from denseness. This is where Zeno tries to say that if lots of things exist, they got to be both limited and unlimited, all at the same time. How does that even work?
This is where Zeno gets really clever.
Yeah.
He uses this idea of denseness. It's this idea that between any two things, there's always another thing. Think about like a line of apples.
Okay, I'm picturing it. A row of apples.
So between any two apples, you could always fit another one, right? And then between those two, another one, you can just keep going.
Yeah, but even if you keep adding apples, the line of apples just gets longer. It's still a bunch of individual apples, right?
That's what we would normally think. But Zeno's getting at something deeper. He's saying that this ability to keep dividing things forever, that means any group of things, it's actually unlimited in a way.
Okay, so how do we deal with that? How can something be both limited, like a certain number of apples, but also unlimited because we could just keep adding more?
That's where something called Cantor's theory of transfinite numbers comes in. It's from modern mathematics, and it gives us a new way to understand infinity. Like it goes way beyond what Zeno was thinking about.
I've heard of Cantor's work, but how does it help us here with the apples?
Well, Cantor showed us that there are different sizes of infinity, and these different sizes can be just as definite as regular finite numbers. Like think about all the points on a line. There are infinitely many, but we can still talk about the length of that line, right? We can even say that one infinity is bigger than another infinity.
So is Zeno's argument messed up because he's assuming that something can't be both definite and infinite at the same time?
Exactly. He just didn't have the right tools to think about different sizes of infinity. Modern math lets us see that a group of infinite things, like those points on a line, can still have a definite size. So his argument about plurality being absurd, it kind of falls apart.
Wow. It's like Zeno was working with this limited view of infinity, and then Cantor came along and gave us this whole new set of tools to see the problem in a totally different way.
Yeah, exactly. Of course, the solution depends on accepting the whole idea of infinite sets, something Zeno might have disagreed with. But for us, looking back with all this new math knowledge, it makes a lot of sense.
All right, this is already making me rethink everything I thought I knew about infinity. But let's move on to Zeno's next attack on plurality.
Oh.
The argument from finite size. In this one, he says that if things exist, they have to have a size. But then that leads to the idea that even something tiny, like a grain of sand, must be infinitely big How is that possible?
It all comes down to dividing an object in half over and over again. Zeno asks us to think about what happens when we do that forever. Does it ever completely disappear?
Well, I'd say it just keeps getting smaller, but it never actually reaches zero size, right?
Exactly. And Zeno argues that if the object has any size at all, no matter how tiny, it must have parts, and those parts must also have some size. And this can go on infinitely.
Okay, but I still don't get how that makes the object infinitely big.
Because Zeno says if you add up all the sizes of all those parts, even though they're getting super small, the total size should be infinite. He's really challenging our understanding of how parts make up a whole.
So how can something like a grain of sand, which is definitely finite, also be infinitely big? It seems impossible.
It does, right? And that's exactly Zeno's point. He uses logic to corner us into this place where our normal understanding of how things work just breaks down. And just like before, we can turn to advancements in math to find a way out of this paradox.
Okay, hit me with that math solution. What do we need to understand here?
This time, our math hero is Cauchy. He did all this important work on infinite sums back in the 19th century.
Okay, remind me about infinite sums again.
Basically, Cauchy figured out a way to understand how an infinite series of numbers could add up to a regular finite value. It seems counterintuitive, but it's a really important part of calculus.
So just because we keep dividing something in half forever, that doesn't mean that all those halves added together are infinite.
Exactly. It all depends on how those halves are getting smaller. Cauchy showed us that some infinite series actually converge. They add up to a specific number.
Ah. So Zeno's making this assumption that any infinite sum has got to be infinite, but that's not always true.
Right. He didn't have the tools to understand how infinite sums could actually result in a finite number. He was working with a much simpler mathematical understanding.
This is so fascinating. It's like modern math keeps giving us these new ways to look at these ancient problems. But before we move on to Zeno's paradoxes of motion, something's bugging me. We talked about how Cantor showed that there were different sizes of infinity. Does that play into this size paradox at all?
That's a great question, and it takes us deeper into the paradox. See, Zeno might have been thinking about dividing the object in two different ways. One way is dividing a specific part of the object over and over. The other is dividing all the parts in half at each step.
Okay, I think I see the difference. In the first one, we're zooming in on a smaller and smaller piece. In the second one, we're making the whole thing have more and more pieces.
You got it. And these two ways of dividing actually lead to different types of infinity. The first way, dividing a specific part over and over, it gives us a countable infinity. That means you can match it up with the regular counting numbers. But the second way, dividing all the parts in half each time, that gives us a bigger kind of infinity, an uncountable infinity.
So there's a hierarchy even within infinity. It's amazing.
Right. And this difference, it's super important to fully understand how to resolve Zeno's paradox. It's not just that infinite sums can converge to a finite number, it's also that there are different kinds of infinity, and the way we divide things determines which kind we're dealing with.
Wow, that's a lot to think about. We're just scratching the surface of these paradoxes, aren't we?
Definitely. But that's part of what makes Zeno's work so great. It makes us think and question our assumptions, and it leads us down these really interesting paths.
Okay, you know what? Let's take a break here. We'll come back and tackle those paradoxes of motion you've been so excited to discuss.
Sounds good to me. Welcome back. All right, get ready because we're diving headfirst into the paradoxes of motion. These are the ones that really capture the imagination, the ones people have been debating for centuries.
I'm ready to have my whole concept of motion shattered. Let's start with a classic.
Yeah.
The dichotomy paradox.
Yeah.
The one where Zeno tries to tell us that motion is impossible. Because to get anywhere, you have to cover, like, an infinite number of distances.
Exactly. So, picture this. You're trying to walk across a room. To get to the other side, first you have to cover half the distance, right?
Right, makes sense.
But before you can cover that half, you got to cover half of that half. So a quarter of the total distance. Before you can cover the quarter, you got to cover an eighth, and so on, forever.
Oh, I see where this is going. It's like that infinite regression thing all over again. You just keep dividing the distance into smaller and smaller pieces.
Yep. And Zeno's saying that to reach your destination, you have to complete an infinite number of these tiny movements. And since you can't actually finish an infinite number of tasks, you can never actually get to the other side of the room.
But I'm doing it right now. I can walk across a room. So where's the flaw in Zeno's thinking?
That's the million-dollar question that's been stumping philosophers and mathematicians for ages. Aristotle, remember him, big fan of picking apart Zeno's arguments. Well, he offered a response that's still relevant today. He said Zeno's only thinking about dividing up the distance, but he's forgetting about the time it takes to cover those distances.
So just like we can divide the distance into halves, quarters, and so on, we can also divide the time it takes to travel those distances. Like half the time for half the distance, a quarter of the time for a quarter of the distance.
Exactly. If you keep cutting the distance in half, you're also cutting the time it takes to travel that distance in half.
So even though there are infinitely many distances to cover, each one takes a smaller and smaller amount of time. Like those fractions of time, they get infinitely small too.
You got it. That means even though there's an infinite number of distances, you can still cover them all in a finite amount of time. What Aristotle is saying is that Zeno's making a mistake. He's treating space and time like they're made up of these separate little units, when they might actually be continuous and infinitely divisible.
So it's like Zeno's trying to apply the logic of counting, like counting apples, to something that's more like, I don't know, a river flowing.
Yeah.
You can't just chop a river into an infinite number of pieces and expect it to stop flowing.
I love that analogy. It really highlights the shift in thinking we need to make to move past Zeno's framework. But even Aristotle, he knew his solution raised some more questions, like, if time is also infinitely divisible, does that mean it's made up of an infinite number of super tiny moments?
Whoa, we're talking about the nature of time itself now. That's getting pretty deep.
It is, and it's a question that's still being debated today by philosophers and physicists. Aristotle tried to tackle this by making a distinction between a potential infinity and an actual infinity.
Oh, yeah, you mentioned that earlier. Can you refresh my memory on what that means?
Sure. So Aristotle's idea was that a continuous line, it's only potentially infinitely divisible. Like, we can imagine dividing it up forever, but those divisions don't actually exist until we, make them. Think of it like a lump of clay that can be shaped into anything, but it doesn't have a definite shape until you actually mold it.
So the possibility of infinite division is there, but the actual divisions only happen when we create them. Kind of like a cake that can be cut into however many slices you want, but it's not actually sliced until you cut it.
Exactly. Great analogy. Aristotle used this to deal with the dichotomy paradox. He said that while a runner's path could be divided into an infinite number of pieces, the runner isn't actually running through an infinite number of those pieces. It's a continuous motion, not like hopping from one point to the next.
So Zeno's paradox works if we imagine the runner stopping at every single one of those infinite points along the way, but not if it's a smooth, continuous motion.
Precisely. It comes down to how we understand space and time. Are they made up of these separate indivisible bits? Or are they continuous and infinitely divisible? These questions go way beyond Zeno's original paradox and touch on the very foundations of physics and metaphysics.
This is blowing my mind. It's like Zeno's paradoxes are these doorways into these bigger philosophical and scientific questions about reality itself.
I like that way of putting it. They force us to question everything and realize that our intuition about how the world works can sometimes be wrong.
Okay, before we get too lost in the big questions about space and time, let's move on to another one of Zeno's famous paradoxes of motion, Achilles and the tortoise. This one's always been interesting to me because it sounds so ridiculous, but then you actually think about it, and it's not so easy to just brush it off.
Ah, yes. The classic race, where the super-fast Achilles can never seem to catch the slow and steady tortoise. It's a perfect example of how Zeno uses logic to create these situations that seem impossible.
Let's remind our listeners how it works. So Zeno starts the race by giving the tortoise a head start. Achilles, being way faster, starts running toward where the tortoise started.
But by the time Achilles reaches that spot, the tortoise has already moved a bit further ahead, so now Achilles has to run to that new position.
But then again, by the time he catches up, the tortoise has moved a little bit more. It's like an endless game of catch-up.
Exactly. And Zeno says this just goes on forever, with Achilles always getting closer to the tortoise but never actually overtaking it.
But we know from experience that if you're faster, you'll eventually pass someone who's slower. So what's the trick here? Where does Zeno's logic go wrong?
The key to understanding this paradox is to see that Zeno's kind of sneakily shifting our focus from overtaking to just reaching the previous position.
I don't get it. What do you mean?
So Zeno's describing these infinite steps where Achilles keeps reaching the point where the tortoise was. But overtaking isn't about getting to where someone was, it's about being in the same place at the same time. The paradox works because Zeno's making it seem like these little steps are the only way Achilles can pass the tortoise.
So it's like he's making Achilles stop at all these points along the way, when in reality he's just running continuously.
Exactly. It's like describing a road trip by listing all the towns you drive through, but forgetting to mention the final destination. The list of towns may be super long, even infinite, but you still get where you're going.
Oh, I see. It's about recognizing that Zeno's description of the race is incomplete.
Hmm.
He's zooming in on these tiny intervals but ignoring the big picture of continuous movement.
Precisely. He's creating this illusion by focusing on these shrinking intervals. Imagine zooming in on a photo further and further. You see more and more detail, but you lose sight of the whole image.
I like that visualization. It's like Zeno's looking at the race with a magnifying glass, focused on this tiny part, and saying, see, Achilles never catches up. But he's forgetting that the race goes on beyond what his magnifying glass is showing.
Exactly. And this is where understanding infinity is important. Infinity doesn't behave like regular numbers. Just because something involves infinite steps doesn't mean it can't be completed in a finite amount of time.
Right, just like the dichotomy paradox. Aristotle's point about dividing time into smaller and smaller pieces, that applies here too, doesn't it?
Absolutely. We can divide both the distance and the time it takes to cover those distances into these tiny fractions. And just like the distances, those fractions of time can get infinitely small.
So as Achilles gets closer and closer to the tortoise, the time it takes to close each gap is getting smaller and smaller, almost like it's approaching zero.
Precisely. And this is where the idea of a limit comes in. Zeno focuses on each individual step, but we can look at the overall pattern and see that the time it takes Achilles to catch up, it approaches a limit, a real number.
It's just like those infinite sums we talked about before. Even though the sum has infinite parts, it can still add up to a regular number.
Exactly. That's how modern math helps us solve this paradox. By understanding limits and how these infinite series can converge, we see that Achilles can definitely overtake the tortoise, even though it seems to involve an infinite number of steps.
This is really making me appreciate how powerful math can be when it comes to clarifying our thinking about these philosophical problems that seem impossible to solve.
It's a beautiful example of how different areas of knowledge can work together and shed light on each other.
Okay, this has been an amazing discussion so far, but Zeno's still got more paradoxes for us, right? Should we take a break and then come back for the final part of our Zeno's paradoxes journey? Okay, we're back. Round 3 of our deep dive into Zeno's paradoxes. I'm still trying to wrap my head around those motion paradoxes. It's crazy how he can take something like just walking across a room or a race and make it this huge philosophical problem.
Yeah, he was really good at showing us the hidden complexity in those things we usually take for granted. He makes us question our intuitions and deal with those big questions that come up when we try to make sense of logic and our actual experiences.
For sure. All right, so are you ready to tackle a few more of these mind-blowing thought experiments?
Hit me with them. I want to see what else Zeno came up with.
Okay, let's talk about the arrow paradox.
Yeah.
This one's always messed with me because it seems so counterintuitive. Zeno's saying that an arrow in flight, it's actually at rest. But how can something that's clearly moving be at rest? It feels like he's just playing with words.
It might seem like that at first, but there's more to it than that. His argument depends on this idea that time is made up of these instants, like a bunch of snapshots. Each one captures a single moment. And he says that at any given instant, the arrow is in a specific spot.
Okay, so if you pause the arrow's flight at any point, it looks like it's not moving. But that doesn't mean it's not moving overall, right? Like a photo of a car doesn't mean cars can't move.
You're getting it. Zeno's assuming that these instants, they have no duration, like points on a timeline with no length. And if an instant has no length, then the arrow can't actually move during that instant. It's like the arrow's frozen for each one of those tiny snapshots of time.
I see how that leads to the idea that the arrow isn't moving, but it still feels wrong. So where's the mistake?
The problem comes when Zeno tries to apply what's true for a single instant to a whole period of time. He's saying that because the arrow isn't moving at any one instant and time is just a bunch of these instants, then the arrow can't be moving at all.
But that ignores the fact that motion has to happen over time, not at a single moment in time. It's like trying to understand a movie by just looking at one frame. You need the whole sequence to see the motion.
Exactly. Motion is about changing position over a period of time. Zeno's trying to analyze motion by looking at these instants that have no time, so it's not going to work. It's like trying to understand a song by listening to each note separately. You lose the melody, the flow.
So it doesn't matter that the arrow is at a specific spot at each instant. What matters is that it's changing position over time. It's the relationship between those snapshots, not the snapshots themselves, that creates motion.
Right. Zeno's mistaking a necessary condition for motion for a sufficient one. The arrow has to be somewhere at each point in time, but that doesn't mean it's not moving from one instant to the next.
This paradox really shows how our language and our intuition can sometimes lead us astray when we're trying to think about these basic parts of reality.
It reminds us that even our most basic ideas about space, time, and motion, they're all up for debate, open to philosophical and mathematical investigation.
Okay, last one. The stadium paradox. This one's a bit more complicated with a bunch of objects in motion. Can you set it up for us?
Imagine 3 rows of identical cubes, all lined up. One row is stationary, and the other 2 are moving in opposite directions at the same speed.
Okay, got it. What happens then?
Let's say that at one point in time, the cube on the far right of the row moving right, it's perfectly lined up with the middle cube of the stationary row. And at the same time, the cube on the far left of the row moving left, it's also lined up with that same middle cube.
So we've got this symmetrical situation where 3 cubes from different rows are all in a line.
Exactly. Now, this is where Zeno gets tricky. He says, because the 2 moving rows are traveling at the same speed, they must have passed each other in the same amount of time.
That sounds reasonable. Same speed, same time to pass each other.
But then he points out that the rightmost cube, the one that's moving right, it's passed all of the cubes in the row moving left, but it's only passed half the cubes in the stationary row.
Oh, I think I see the problem. It's traveled a different number of cubes in the same amount of time, even though they're moving at the same speed.
You got it. And that seems like a contradiction because it implies that half a time is equal to the whole time.
I'm not sure I follow that part. How does that work?
Well, Zeno's assuming that the number of cubes passed is directly related to how long it takes to pass them. Since the rightmost cube passed twice as many cubes in one row, he says it must have taken twice as long, even though we know the times are the same.
It's like saying if I walk past 10 people in a minute, and you walk past 5 people in the same minute, then my minute must be twice as long as yours. That doesn't make any sense.
Exactly. So most people who try to understand the stadium paradox, they say that Zeno's making a mistake about relative motion.
Okay, so how does relative motion fix this?
The rightmost cube passes twice as many cubes in the row moving left because it's moving at twice the speed relative to that row.
Ah, so it's not just the speed of each row on its own, but their speed compared to each other.
Right. When you take relative motion into account, the contradiction disappears.
So Zeno's paradox comes from this little oversight. He's not thinking about relative motion, and that leads him to this conclusion that doesn't make sense.
It's a pattern we see a lot with Zeno's paradoxes. He sets up these situations where he focuses on one specific aspect of motion or plurality, and then he creates a contradiction by leaving out other important factors.
It's really clever the way he shows the limits of our intuition when we try to understand these basic concepts.
And some people think there might be even more to the stadium paradox than just a misunderstanding of relative motion. They say Zeno might actually be arguing against the idea that space and time are made up of tiny, indivisible units.
That's an interesting take. How does that tie into the paradox?
Well, if we imagine that space and time aren't continuous but are made up of these tiny units, then we run into problems with how things move.
Right. If space is like a grid and time is like ticks on a clock, then how does anything move smoothly from one square to the next? How does it move from one tick to the next without ever being in between?
Exactly. If space and time are made of these separate units, then we need a new way to explain motion that doesn't rely on things moving continuously through space and time.
It's like trying to make a movie where each frame is completely separate with no smooth transition between them. It would be a jumbled mess.
Right. So even if Zeno wasn't directly trying to critique that idea, the stadium paradox shows how hard it is to make that idea of atoms of space and time work with our experience of smooth, continuous motion.
This is incredible. It's amazing how these paradoxes from thousands of years ago are still bringing up such important and relevant questions about the nature of reality.
That's what makes Zeno's work so powerful. He wasn't just playing around with logic. He was making us confront these deep mysteries of existence.
So after all this, have we actually solved these paradoxes?
I wouldn't say solved exactly. They're still debated, and they still inspire philosophers, mathematicians, and physicists. We've explored some pretty convincing solutions using modern math and by understanding things like continuity and infinity better. But the questions they raise about space, time, and motion, those are still very much alive.
It's like every solution just leads to new questions, pushing us to understand these fundamental ideas even better.
Exactly. And maybe that's Zeno's greatest contribution, not giving us all the answers, but making us keep asking the big questions.
Well, I think it's safe to say that Zeno's given us a lot to think about today. Thanks for joining me on this journey through the history of philosophy and the depths of mathematics.
It's been my pleasure.
And to everyone listening, keep thinking about these paradoxes. Keep questioning your assumptions and exploring the mysteries of the universe. Who knows? Maybe you'll be the one to make the next big breakthrough that sheds new light on these ancient puzzles. Until next time.